Alright, welcome back, guys. Now we're going to be looking at applying those properties of logarithms to expand these logarithms. So if you look at some of these logarithms and their arguments, they've got a lot in them, okay? You can look at this logarithm here. It's a product. We've got these three factors being multiplied. We want to basically expand that out, okay? And then this second logarithm, it's got a lot going on here. And then furthermore, this one, okay? So our strategy here is to kind of pick these apart. So that's what we're going to do. So if you look at this example, it says we want to rewrite or re-express this logarithm as a sum or difference. Well, technically sums or differences of logarithms. So in other words, that just means expand this, okay? And to do this one, we're going to utilize the product rule, because if you notice, the argument of this logarithm is a product. It's a product of these three different factors here, a cubed, b to the sixth, and then c. Okay, so the first thing that I'm going to do, I'm going to start by writing three separate logarithms. And in each of those logarithms, we're going to have one of these factors. So this will be the natural log of a to the third. And remember, because we're using product rule, we'll be separating these logarithms with addition. Okay, so the natural log of a to the third plus, then we'll have the natural log of b to the sixth plus, and then finally the natural log of that last factor, which is c. Okay, so that's my first step. Now I can take one more step here, and I can use the power rule. Okay. Because if you notice, the arguments of two of these logarithms have a power. Okay, so the power rule just basically says that we can take that power and move it out in front of the logarithm. And so if I do that, this will become 3 times the natural log of just a plus 6 times the natural log of b plus, and there's not really anything I can do with that last logarithm because c doesn't have a power, well, other than 1. Okay. So typically when you're expanding these logarithms, guys, the power rule will be the last rule that you utilize. If any of these arguments have powers, those powers get moved out front, okay? So this is like a product of 3 and the natural log of a. So anyway, we have completely expanded this natural logarithm here. Alright, now we're going to do the same thing with example 12, except it's going to have an extra step to it. Okay. So I'm looking at this. This is the natural log of b. The one thing I notice is that this whole thing right here in this argument, this is a quotient. So my first step here is going to be utilizing or applying the quotient rule. Alright, so let me come over here. And I'll start out by saying this is going to be log base b of just the numerator. Okay. So remember, with the quotient rule, when you go to separate the logarithms, you're separating them with subtraction. So this will be the quotient, or excuse me, the log base b of the numerator, which is x to the fourth. No. Computer froze again. X to the fourth, y to the fifth, okay, minus log base b of the denominator, which is n cubed b to the seventh. So that's the first thing we can do. So there's kind of an order in which you utilize these rules. typically it goes quotient rule, product rule, and then power rule is the last one. Now, obviously we didn't use quotient rule in this first one because this was not a quotient. But if you do have a quotient, then you'll use quotient rule to split that up first using subtraction. Okay. And then you're going to use product rule, because what we have now, inside each of these two logarithms, we have products. Okay, so now what I need to do is use the product rule. I'll write this in the notes. Okay, to split up these products here. So then this will become the natural log. I don't know why I keep saying natural log. Log base b of that first factor, which is x to the fourth, plus, okay, because we're using product rule, remember, log base b of the second factor there, which is y to the fifth, minus, you're going to bring down that minus sign, and then you're going to use product rule again with this logarithm. Now, technically what happens is you split apart that logarithm, so this becomes log base b of n to the third plus, because we're using product rule, log base b of that second factor, which is b to the seventh, but because there's a minus sign in front of this logarithm, you end up having to distribute this negative here. Okay, and so that's going to actually make this last logarithm negative. And so, let's see, I'll draw this in the notes, or denote this in the notes. Okay, well, so this third logarithm will become a negative, and so will that fourth logarithm. So I could just rewrite all this stuff real quick. Log base b of x to the fourth plus log base b of y to the fifth, and then minus, I can take the parentheses away now, log base b of n to the third minus log base b of b to the seventh. Okay, and then you just keep going. So now I've utilized the product rule, so now the last thing that I can do is the power rule. Okay, oops. So the power rule just says that if I have powers in any of these arguments, I can just move them out in front. So if I do that, this will become 4 times log base b of x plus 5 times log base b of y minus, move that exponent out, 3 times log base b of n minus, move that 7 out, 7 times log base b of b. Okay, and then this one has one extra step, because this last logarithm here, guys, we can simplify. Log base b of b is 1. I don't know if you recall, but anytime the base of a logarithm is the same as the argument, it's just 1, because you're essentially asking yourself, b to what power is equal to b? Well, it's the first power. Okay, so this will be, let me circle it here. All of this will turn into a 1. Okay, and so 1 times that negative 7, it's already here, will just remain negative 7. So then I can just, I'll recopy the rest of this real quick. 4 times log base b of x plus 5 times log base b of y minus 3 times log base b of n, and then minus 7. Okay, so you're going to see something like that in your homework. We have this last little extra step right here. All right. A lot of this, guys, is just a lot of mechanics. Okay, and the more you do it, the better you get at it. All right, let's look at example 13. All right, so with example 13, You can see that this is a quotient. However, I first need to somehow manipulate this, because overall this is not a quotient, but rather a cube root. So I need to use that property that I showed you from above. Oh, here it was. Yeah, right here. I need to use this property to express this cube root, or this radical right here, as an exponential expression. Okay. Well, what you can do is think about that, okay, all of this is being raised to the first power. So then I can rewrite this as log base b of that whole quotient there. I'll just rewrite it real quick. Oops. That's d to the 10th. b to the 7th, a to the 5th. And then this will all get raised to the index here is 3, the exponent is 1, so this will become the 1/3 power. Okay. And then the next thing that I can do before I can really look at this as a quotient is I need to, in a sense, distribute this power 1/3 to all of these exponents that are in here. Okay. But to do that, I use the power rule, which means I multiply all these exponents by 1/3. This will become log base b of c to the 11/3. Basically, it'll just give them all denominators of 3. D to the 10/3 over b to the 7/3 and then a to the 5/3. Okay, so all of this now is a quotient. So this one had an extra couple steps at the beginning to take care of this radical. Okay, you rewrite the radical as an exponential expression, and then you distribute this exponent, and now I've got just a quotient right here. So now I can then proceed the way I did the last one. Split this apart using quotient rule, and then use the product rule and then the power rule. Okay, so this one's got an extra step or two. Like I said, a fair amount of work, but okay, so the quotient rule says that this will split into two logarithms, the logarithm of the numerator minus the logarithm of the denominator. So let me go ahead and write that out. I have to kind of write small here so that I have enough room. So this will become log base b of this numerator right here, c to the 11/3 times d to the 10/3 minus log base b of the denominator, which is b to the 7/3 times a to the 5/3. Okay, so I've utilized quotient rule. I've split it into two. Now I'm going to utilize the product rule. Okay, because I have products in each of these two logarithms. Okay, so this will become log base b, it's just a lot of writing. Log base b of c to the 11/3 plus log base b of d to the 10/3. And then, guys, when I split this one apart using product rule, I'm going to go ahead and distribute the negative. So this will become a minus log base b of b to the 7/3, and then that minus will turn this next one into a negative. Log base b of a to the 5/3. Okay. All right, and then now I can use the power rule. The power rule just says that if any of these arguments have exponents, I can move those exponents out in front. So this will become 11/3 times log base b of c, drop down that plus sign, 10/3 times log base b of d minus 7/3 times log base b of b, which this is just going to turn into 1 again, minus, oops, I forgot to move the exponent out, 5/3 times log base b of a, okay? And then your last step would just be to replace log base b of b with 1. And so this third logarithm here will turn into negative 7/3 times 1 is just negative 7/3. So we'll end up with a final answer. I guess I'll just rewrite all this again. That would just become 7/3, and then finally minus the 5/3 times log base b of a. Okay. So guys, refer back to these 3 examples in which you're expanding these logarithms when you're working on your homework. Because now what we're going to do is, instead of expanding them into several individual logarithms, we're going to be going in the opposite direction. We're going to be putting them back together. So we're going to be moving the powers back in, okay? And then if we have logarithms that are separated with plus, we're going to condense that back into a product. This one you have to kind of pull out the negative and then rewrite it as a product, and then piece these last 2 together because they're separated with subtraction into a quotient. Anyway, but all right, let's take a look at example 14. Alright, example 14. Typically the way you do these is you go in the reverse order. So instead of the power rule being the last thing that you utilize, it's the first thing. You move the powers back in. Then you, well, here you probably need to use, well, let's just look at this next one, okay? All right, this says to express as a single logarithm and simplify if possible. Well, if you have numbers in front of your logarithms, those are going to become exponents, okay? So I'm going to start off here by moving those back in. Okay, so really only 2 of them have numbers in front, so I would be utilizing power rule. Alright, so this will become log base b of x to the 5th minus, and I'll leave that second one alone, log base b of y plus, and then I'll move that 1/4, log base b of z to the 1/4 power. Alright, then what I'm going to do, I notice here there's a minus sign. So I'm actually going to combine these 2 using the quotient rule. Right? Because when you have 2 logarithms separated with subtraction, that means you can condense them into 1 and make their arguments a quotient. Okay, so quotient rule. So this will become log base b of x to the 5th will be my numerator over just y. Okay, and then I'll rewrite the rest of this. I still have the plus log base b of z to the 1/4. And now I've condensed this down to 2 logarithms. So now I need to condense these 2 logarithms down into just 1. Well, they're separated with addition, so we're going to have to utilize the product rule. Okay, so this will become 1 log base b of, and we're going to multiply these arguments when we put them back together. it'll be x to the 5th over y times z to the 1/4. Okay. And so when you're multiplying here, it's really like the z to the 1/4 is in the numerator. And so you could write this as, or we express it as log base b of x to the 5th z to the 1/4 over y. Okay, so that's your argument. Basically, guys, what's happening is if you have a negative in front of a logarithm, that argument will end up in the denominator. And if you have a plus, or any positive logarithms like this first one and this last one, their arguments will end up in the numerator, okay, when you're done. And there's one last thing I can do here. Can't really simplify this much, but I can re-express z to the 1/4 using a radical. If you remember, that will become the 4th root of z to the 1st, or just the 4th root of z. So I can re-express this as log base b of x to the 5th times the 4th root of z all over y. Okay. All right, let's try example 15. Now, example 15 looks a bit simpler because it's only got 2 logarithms. The more logarithms there are, the more work there is when you're condensing. So example 15, it says express as a single logarithm and simplify. Okay. All right, well, I think what I'm going to do here before I get started is I'm going to let me do this with my stylus. Re-express this radical, the 3rd root of x to the 4th, as an exponential expression. Re-express it as x to the 4/3, okay, using that property that we've been alluding to. So if I were to do that, then I could just rewrite this real quick. Be the natural log of x to the 5th minus 2 times the natural log of x to the 4/3. Okay. So now I'll go about using the power rule. So the power rule just says, now that these both have powers, I can just move those out in front. Okay, so this will become 5 times the log, or the natural logarithm of just x. But now when I move this 4/3 out here, I actually have to multiply it by 2. So 2 times 4/3 will give you 8/3. Okay. Oh wait, I'm thinking about this in the opposite direction. No, I'm moving I'm moving the 2 back in, okay, but it becomes the exponent of x to the 4/3. So in any case, I have to multiply 4/3 times 2, which is 8/3, okay. So this will become minus, oh, wait a minute, what am I doing? I've got myself disoriented here. If I'm condensing, yeah, I just instinctively started to expand this by moving the 5 out, but no, we're in condensing mode, okay? So I need to move the 2 back in, and I need to leave this one unchanged. So sorry about that, guys. Okay, minus, when I move basically the 2 back in, it's like I said over here, okay? I'm going to multiply the 2 times the 4/3, which will be 8/3. So this will become the natural logarithm of x to the 8/3. Okay, sorry if I confused anyone. Yeah, so again, the first thing I did is I re-expressed this radical as an exponential expression. And then using power rule, we'll move the 2 back in. Okay. So this will become x to the 8/3. And now, since these two natural logarithms are separated with subtraction, I can use the quotient rule to combine them into one. So this will become the natural log of x to the 5th over x to the 8/3. Okay. But I'm not finished because I can simplify this. These bases are the same. They're both x's. So you can subtract those exponents. 5 minus 8/3. You might want to do this in your calculator. Okay. 5 minus, if I hit alpha and then y equals, type in 8/3. Okay, so I'm just again using the online version of that TI-84 emulator app. It'll give me my answer. It's a fraction, it's 7/3. Okay, so that'll be the power of x. So this will become a natural logarithm of x to the 7/3. And then finally, if I want to, I can express that as a radical. That'll be the natural logarithm of the cube root of x to the 7th. Okay, so kind of a lot going on in this one. But it illustrates several things that you need to know. Alright, let's do this last one. Okay. Example 16. Again, we're going to condense these two. We've got two natural logarithms again. We've got a lot going on in their arguments here. First thing I'm going to do is just, there's no numbers in front, okay, so I don't need to use the power rule. I'm not moving any powers back in. The first thing I'll do will be to use quotient rule. Okay, so this will become the natural log of that 3x plus 1. That will become our numerator. And then the 3x, I don't know why I'm keeping that in parentheses. That trinomial, which is the argument of the second logarithm, will become our denominator, 3x squared minus 5x minus 2. Okay, so this fraction now, or this quotient, is the argument of my logarithm. Now we have condensed it into a single logarithm now, but the argument in this logarithm can be simplified. And this takes us back to working with rational expressions. Okay. The only way to simplify this, guys, is if I can factor this denominator. If I can factor it such that one of its factors is a 3x plus 1, then I could divide those out, and that'll simplify this. And looking at this trinomial here, it's quadratic, again. I think it is factorable, but we have to use the AC method because there's a number in front of the x squared. So most of the work in this one is going to be factoring this. Okay, so I'm going to kind of come over here to the side. 3x squared minus 5x minus 2. And you have to remember, the AC method means we multiply a times c. That's negative 6. Factors of negative 6 that add up to negative 5 are negative 6 and 1. And so with the AC method, and put this in the notes, you bring down the first term, you rename the second term using those two numbers you found, negative 6 and 1. So it becomes negative 6x plus 1x, okay? And that's still negative 5x, and then you drop down your last term. And now, because you've got exactly 4 terms, you factor by grouping. So this problem is just as much an exercise in factoring as it is anything. Well, I'm looking at these first 2 terms, and I can see a 3 and an x common to both of them. So I'll take that out. If I do, it's just going to leave me with an x left from this first term, and it'll leave me with a minus 2 left in that second term, okay? Plus, now when we come to our last 2 terms here, you may say, well, they have nothing in common. We can always take out a 1. And when we do, that'll leave them unchanged. That'll just be an x and a minus 2, okay? And so now you can see that we have x minus 2 common to both of these terms. So we'll take that out, and that will leave us with 3x plus 1, just as I suspected, because I had a 3x plus 1 in the numerator. So I figured that was kind of the objective of this problem, as much as it was convincing. Okay. So what happens here? Well, I can simplify by dividing out. I got a pair of, actually I wanted to select a different color to do that. I have a pair of common binomial factors. And so remember, when you have nothing left in the numerator, there's always that understood 1 up there. Alright, so this will equal the natural log of 1 over x minus 2. Okay? Interestingly, if you recall our study of rational functions, because we divide out this binomial here, the domain, this function could, I'm thinking about, kind of like what its domain would be, and its domain is going to have 2, well, the rational function here, the domain would have 2 restrictions. The actual logarithmic function would have, well, those 2 restrictions, and then an entire interval of numbers restricted, because remember, we can't take the logarithm of a negative. So, but anyway, we're not going to get into it that deeply. But I was just kind of thinking, like, if we were to graph this, would it have a hole in it somewhere? But anyway, guys. Alright, so you've got a fair number of homework questions from this section, so just take your time. I tried to include an example of all the nuances that you're going to see in the homework questions. Okay. Alright, so anyway, I'll see you in 9.6, where we'll actually be solving equations that have logarithms in them. They'll have exponential functions or expressions in them, logarithmic expressions, but they'll be equations. So exponential and or logarithmic equations. We're going to look at how we can solve those. Okay, it's not as easy as add or subtract something from both sides of the equation and isolate for x. Okay, so anyway.